So we are going to try to take the things that we've been talking about with limits and with continuity and solve the problem that we've started out with, and that problem being finding the slope of the tangent line to a curve. So how do we find out what the slope is to a curve? So just before we do that, I just wanted to quickly review the slope of a line. So you guys know if you have 2 points that the slope is defined by this formula, delta y over delta x, rise over run, y2 over minus y1 over x2 minus x1, and it represents the rate of change of y with respect to x. So that is new wording for you, but essentially what it's saying is as x changes by this much, y is changing by this much. That's what the slope is telling you. So if the slope is 2, it means that every time x changes by 1, y changes by 2. And that with respect to x is going to become important throughout our conversations with calculus. And then we know if the line rises to the right, the slope's positive. If the line rises to the left, the slope's negative. And then our horizontal slope is when you have just y equals, so there's no change, there's no m. And then if the line's vertical, then you have x equals, and so the slope's undefined. So because that's true of slope, that's also true of derivatives. There are times where the derivative is not going to have a value. There are times when the derivative is going to have a value of 0. There's going to be times when the derivative has a positive value or a negative value. And there's going to be times, most of the time, where we're going to actually derive a function that describes the slope. Because if you think about a curve, it's kind of going like this, the slope changes. And so we're going to try to find out how that happens. So you have to bear with my computer. It's very slow this morning, but hopefully it will change slides here. What we're going to try to do is we're going to try to take our knowledge of slope and our knowledge of limits and marry them together to find the slope of a tangent line. So you know the definition of a tangent line. The slope of the tangent line is the slope at one point, right? Because the tangent line touches the curve only at one point. So the problem arises that how do I get the slope at one point? Okay, and so what I'm going to do, and I've already drawn this, imagine that this blue line is my curve. Okay, and essentially what I'm going to do is I'm going to pick a point P where I want, maybe I'll just redraw this so you can sort of see how I've built this. Again, assuming the computer cooperates. But we're going to take a point P. We're going to say I want the slope of the tangent line at P. Because this tangent line only has one point where it touches the curve, that's a problem for us, right? So we're going to, okay, so let me just redraw this. Assume this is my curve, okay? I want the slope, let's say right here, right, at this point P. So what I'm going to do is I'm going to pick a point Q. Let's say I put Q here, and I'm going to draw a line through PQ. And I'm going to say that that, which is called a secant line, is an approximation of the slope of the tangent line. If I draw the tangent line, let's just pick a different color. The tangent line is going to look something like that, right? So the slope of that secant line is not the slope of the tangent line, but it's an approximation. Now, if I move Q closer to P, so let's say I move Q here, all right? So I'm going to move Q up there. If Q is close to P, then if I draw a line through those 2 points, it becomes a much better approximation of the tangent line. It's not exactly the same, but it's a much better approximation, right? And so what we're trying to do, basically, we're going to try to continue to move the point Q closer to the point P. That's our goal. Okay? And as we do that, you can probably see how limits are going to become important because we're going to try to make the distance between P and Q smaller and smaller. So we're going to try to take the limit as that distance approaches 0. That's our plan. So what we're going to do is we're going to define our point P, if we just sort of zoom in, as x and f of x. All right, same thing as y, but it's the function at x. And then we're going to say the distance between P and Q, I'm going to define that as h. So that means that if I start at x and I go h more, I have x plus h as my x value. and that means my y value is f of x plus h. Okay, so then I say, okay, what's the slope between those 2 points? And the slope formula we just looked at was y2, which is f of x plus h, minus y1. So if you want to sort of label these, maybe just with a different color so you can see what I'm doing. That's y2, that's y1, and then that's x2, and that's x1. Okay, so my slope becomes this, f of x plus h minus f of x divided by x plus h minus x. And I can put this in brackets. I don't need to, but just so you can sort of see, there's x2. So there's y2, y1, there's x2, and there's x1. So what I'm going to do, you'll notice, is on the bottom, x minus x will simplify. I can't do anything to the top. It just stays like that. But this x is canceled on the bottom, so I just end up with this. All right, that is the slope of my secant line PQ. So if you're following what I'm doing so far, now what I want to do is I want to say, okay, what happens when the point P and the point Q actually become the same point? So what is the slope going to approach when h, the distance between P and Q, approaches 0? And that's where the limit comes in. So what we're going to say is the slope of the point P, the slope of the tangent line of the point P, is the limit as h approaches 0 of the slope of PQ. Okay? So that is the definition, the limit definition of the derivative. That's what it's called. That is going to give us our derivative function. So in terms of notation, there are 2 ways to represent that. Okay? The first way is using Newton's notation. This is Newton's notation. You have a prime there, so it's not f to the 1, it's f prime. It's like an apostrophe. All right, so we call that the derivative, and it's defined in Newton's notation. There are 2 guys that came up with calculus. Some people argue that Leibniz stole it from Newton. That would be me. Some people argue that Leibniz came up with it and Newton stole it, and some people argue that they came up with it independently. All right, I'm very much a Newton man, but who really knows? You can read about it. Bored on a Saturday night, Friday night, need something to do, look into the origins of calculus. Fascinating stuff. But this is Newton's notation. This is Leibniz notation. So Newton's notation, if you're taking the derivative, you just put f prime of x or y prime, depending on if it's y equals or f of x equals. Leibniz notation says d of f of x over dx or dy over dx. So we're saying the derivative is dy over dx. Okay, so we're defining that. That gives me the general limit definition of the derivative. That's it. Okay. The other option is if you're trying to find the derivative at a particular point, we can define it using this. So if we want the slope of the tangent at a point A, we can say that it's the limit as x approaches a of f of x minus f of a over x minus a. The difference is that this formula will give you a number. It's a numerical answer. And that number tells you the slope at a particular point. So the slope might be 5, and then over here it's 2. You would have to do the calculation twice. Okay. This is the more general one, and it basically tells you the derivative function. Okay. So this gives you the value of the derivative at a particular point. This gives you the general expression for the derivative. Okay. So we'll show you both, but let's do an example, first of all, of just finding the derivative. So here's what the question says. It says find the derivative of the function y equals x squared plus 3. And I want to find the derivative, so I use the derivative definition. Okay, now this guy is a composite function. All right, and we talked a little bit about composite functions last year, but basically what you're going to do is wherever there's an x, okay, you're going to put an x plus h. So this is x squared plus 3. So f of x plus h becomes x plus h squared plus 3. Okay? So wherever there's an x, that x gets replaced with x plus h, and everything else stays the same. Then it's minus the function. So there's my function, x squared plus 3, all divided by h. And what you'll notice is if you let h go to 0, you always get, if I let h go to 0, f of x minus f of x. I don't know why that's drawing in those black lines, but anyway, over 0. So what that means is, let me just try to write this again because it doesn't really look like anything. And see if we can avoid the black line. So if we let h go to 0, we get f of x minus f of x, and then it's all divided by 0, and that gives you 0 over 0, and we know from our knowledge of limits that that means it's an indeterminate form, so we have to do something. Generally, what we're going to do with these, if they're polynomial functions, is we're going to expand. So I'm going to expand x plus h squared, okay? And that gives me, I'm just going to try to take these out for a second, put them back in a moment. X squared plus 2xh plus h squared, and then plus 3, and then minus x squared and minus 3, if you remove the bracket from this. And then what happens, if we put those back in, is the x squareds and the 3's cancel. Okay, because you have x squared minus x squared and 3 minus 3. And so what you end up with is 2xh plus h squared over h. And what you'll notice is now the h will cancel because there's an h in each term. So if I factor out the h, I get 2x plus h left over. The h's cancel, and now my discontinuity is gone. Now I don't have 0 over 0. So my problem is gone. So I can let h go to 0. And when I let h go to 0, that's going to disappear. So I'm going to just end up with 2x. Okay? So what that tells me is the derivative of x squared plus 3 is 2x. If I want the slope of the tangent at a particular point now, what I do is I take that point and plug it in to my derivative. So if you look at something like what's the slope as x approaches 2, it would be 4. Okay? Computer's freezing again. If it was 5, if I want to know when x was approaching 5, I'd go 2 times 5, that would give me 10, and so on. So I'm going to leave that there, and then I'll produce a second video that just gives you more examples.